Hey everyone. I want to introduce you to the chi-square distribution and some chi-square hypothesis tests. I'm not really going to do much in the way of actually presenting hypothesis tests. I'm just going to use this video as a sort of an overview of what chi-square is. So let's get started. So let me share the notes up and we'll get going. So here's the idea. This is the notes that you can find in the link in the usual place. So first things first, this is not an X, this is a Greek letter. It's actually a Greek C. It's chi. So this is called chi-square. It's just the name of the distribution. It's not pronounced, it's spelled chi, but it's pronounced chi. So it's called chi-square instead of chi-squared. I don't know why. I've never known that particular thing. Anyway, so here's the basic idea. What we learned about last week or in last set of videos was two-sample hypothesis testing. We learned about for qualitative data and for quantitative data, right? You get your two-sample T, your two prop Z, paired T. What we're going to learn now in this set of videos is about chi-square, which is more than two. It's not more than two samples necessarily. It's still two samples, but it's going to be qualitative data with more than two categories, right? So up until now, what we've done is like, the question we would ask with qualitative data would be something like, do you approve of the president's performance? Yes or no, right? Only two options. But that's not really how a lot of real world questions go. A lot of other very important questions are going to have several different categories that something could fall into. And so the question is, well, how do we do a hypothesis test on that when everything we're doing is like yes or no, use binomial or use the normal approximation of the binomial, and chi-square is how you do that. So let's look at these. So here's the basic idea. So if you've got something, this is just a really basic question here, but if you got something with several different categories and you want to see if those categories, the percentage of data falling into each of those categories in your sample is different enough than you were thinking to make you want to reject the null hypothesis, that's what chi-square tests do. I think I said that a little bit awkwardly, but the basic idea is this. For some tests, we're actually going to have three different tests, four different tests, but two of them, the middle two, are kind of the same. So the first one we're going to do is a goodness of fit test, and then we're going to learn about homogeneity and independence, which some people just lump together into one test called a chi-square test of association. Your book does it a little different. It splits them out into two. The difference between them is largely semantic. It's not actually that big a deal, but I'll do it like your book does it, and we'll split them into two, but I'll do it by teaching you just independence and then saying, well, and homogeneity is pretty much the same thing with this minor difference. And then the third/fourth one that we're going to learn is called a chi-square test of a single variance. And it turns out that variance follows a chi-square distribution, unlike the mean, which follows a normal distribution, or the sampling distribution of the sample mean follows a normal distribution. The sampling distribution of the sample variance follows a chi-square distribution. So we'll use it a little bit differently there at the end. But that first one that we're going to do, the chi-square test of goodness of fit, is basically this one, which in the goodness of fit video, I'll actually go through this example here. But the basic idea is this. Let's say you have a claimed percentage of eye color, right? Claimed percentage of people falling into certain eye colors: blue, green, light brown, dark brown, black, right? So by the way, just a heads up, this is a vast oversimplification of eye color. When I originally went to make this example, I looked up how like knowledgeable people define eye color, and there's a lot of categories. There's way more than this, and it made for a messy, confusing example. So I'm just fudging it and using really simple ones here. So I've just got I got four categories: blue, green, light brown, dark brown, or black. Iris color. I should say iris color rather than eye color, but that's okay. And then let's say we have a study that claimed these were the percentages they found: 37, 18, 14, and 31%. And then we do a sample, and these are the numbers that we get. Well, the question then becomes, okay, do we believe the original claim or not based on this data? And how would we even evaluate that? Well, that's what chi-square is all about. So that's what I want to introduce to you here, is that's what we're going to do. We're going to see, are these numbers different enough from those percentages for us to think that the percentages are wrong, right? And so that's the way we're going to do our hypothesis test. Later, that's the basic idea. We'll explain. It gets a little more complicated when we get into independence and homogeneity, but I'll explain the differences then. But that's the essential idea. Is if we're expecting a certain thing and we get this data, is this data different enough from what we expected to make us think that our original expectations were wrong, right? Just like a normal hypothesis test, our null hypothesis is going to be the expectations, and then we're going to gather our data, and we're going to see if our data agrees enough with those expectations or disagrees with enough with those expectations for us to think that the original guesses were incorrect. So that's how these tests are going to work. The math is going to get a little fancy in the second set that we're going to learn about, but it's relatively straightforward for goodness of fit. So anyway, a couple of facts about chi-square distributions that we're going to use here. So your degrees of freedom in a chi-square distribution is k-1, where k is the number of categories. So for instance, this test right here we've got 4 categories, so it has 3 degrees of freedom. So chi-square with 3 degrees of freedom. Still, it's not n-1, like it's not number of samples -1. It will be when we get to the final test, the test of single variance. But for right now, it's just categories -1. And it'll be slightly different than that when we get to the second set of tests. Here's 2 interesting facts that you might be a little bit helpful, but not really as much as you might think. This one I'll quote a little bit, that the mean of a chi-square distribution is equal to its degrees of freedom. So the mean of the distribution for this test would be 3. And we'll see how we calculate that number and just calculate a test statistic in just a second. And then the standard deviation that you absolutely do not have to know, but I'm just including it as kind of a curiosity, square root of 2 times degrees of freedom. Okay. So here is how you do the calculation. This is how you get your test statistic. Like, this is where the chi-square thing comes from. What you do is, so O stands for observed and E stands for expected, and E again stands for expected. And then this symbol, I don't know if you guys know this, we've used this a little bit in class before, but this means add everything up, right? This is actually a capital Greek sigma, which sigma is a Greek S, and so this is an S because it stands for sum. So we are summing up all of this stuff. So what we're going to do is, over all the cells in the table, we're going to calculate observed minus expected, square it, and divide by expected. So observed is how many things you found in that category. Expected is how many things you expected to see in that category. And we're going to take their difference. So in other words, how far apart was our observation from our expectation? And we're going to square it and divide by our expectation. And I'll explain why in just a second. But first, let me go back up here and just say, so here is our claimed percentages. Those are our expectations, almost. Those are what percentage of our sample size we were expecting to see in that category. These are our observations. So the observed counts are always whole numbers, and they're always they have to be given. They're your data. So for instance, if we observed 300 total people, and it was actually the case that 37% of all people, or of all Americans, had blue eyes, then we would expect 37% of our sample to have blue eyes. And so we would find 37% of 300, which is 111. Yeah, it's 111. So in other words, our expected count would be 111, and our observed count was 97. So what we would do is we would go, well, I zipped way past it. We would go here and we would say our observed count was 97 and our expected count was 111. So we would do 97 minus 111, and we would square that, and then we would divide it by 111. Then we would do that for each of these cells. And by cells, I mean like these guys right here. Right, so I have 4 cells. And each of those has an observation and an expectation. You might say, well, don't you mean we have 8 cells? Yeah, kind of, but not really. So what the idea is that we have, I'm thinking of like a cell for blue, and then we have an observation and an expectation for that cell. So it's a little bit confusingly named, but that's what it is for goodness of fit. It's one cell per category. Okay, so a couple things that I want to point out here about chi-square distributions. Number one, this number is never negative, it's always positive, because although O minus E itself might be negative, when you square it, it'll become positive, right? Like in the example I just had, 97 minus 111 is 14, or is negative 14, but then when we square the negative 14, we get positive 196. So every cell, of which there are 4, would have a positive contribution, or at least 0, right? O minus E could be actually 0. But that's the smallest it could ever, that's the smallest O minus E squared could ever be, is 0. So every cell has a non-negative contribution. So this number that we get when we're done adding them up is always positive. That means that there are no negative chi-square values. They're all positive. The farther apart O and E are, the bigger this number is. So if O minus E, if observed and expected, so in other words, if the observed value in a cell and the value we expected to see in that cell are close together, that provides very little evidence for us to reject the expected values, right? So our expectations were basically met if our observations were close to them. And so that would cause us to not want to reject the null hypothesis. In addition, the farther apart O and E are, the bigger this calculation is, or the bigger this number is. And so the more we want to reject the null hypothesis. So when O and E are far apart, in other words, when what we observe is very different from what we expected, that makes us want to reject the null hypothesis. It also makes this number big. Consequently, the bigger each of these numbers is, and the bigger the overall total is, the more we want to reject the null hypothesis. So all of our chi-square goodness of fit tests and independence and homogeneity tests are right-tailed. There are no left-tailed versions because bigger chi-square means more wanting to reject the null hypothesis. That changes when we get to the last one, which I'll talk about in that video. But for now, just bigger chi-square means more rejecting the null hypothesis. And bigger chi-square comes from O and E, observed values and expected values, being far apart, which is exactly what you'd expect, right? When your observations and your expectations don't match, it makes you think that your expectations weren't right. We're going to be doing this using a couple of things. There's a chi-square CDF in your calculator, which of course we will use. And then there's also a test function in your calculator, which we'll also talk about. There's also a chi-square GOF function, which is the first of the tests, goodness of fit, that we're going to talk about, which I will in general not be using, not because it's not good, although it's actually a little awkward to use. It's surprisingly, it's much easier to do the harder test, which is kind of funny. But mostly because not all the calculators have them. So there are some TI calculators that don't have chi-square GOF. So I'm just going to show you guys how to do that one by hand, essentially. And then I promise on a test, I will keep them relatively short. I won't give you something with like 20 categories. It's going to take you all day to calculate. By hand, I'll keep it to like 3 or 4. Yeah, I think that's all I want to say about the intro. So just to recap, the basic idea is we calculate how many things we expected to see in a certain category, and then we compare that to how many things we actually saw, and we do that like this. This is our calculation for that. And then we add up all those things, get a chi-square test statistic, and just like with goodness of fit, or excuse me, just like all of our other hypothesis tests, We graph it on our sampling distribution, calculate our p-value by finding the area that is more extreme than our observation. Yeah, we'll see all that when we get to the examples, but just realize that the basic idea of the hypothesis test is still the same as it always was. We're comparing our data to what we thought was going to happen, right? The null hypothesis. And if the data disagrees enough with the null hypothesis, then we reject the null hypothesis. That's still what we're doing. It's just that the way we're calculating the probability is a little bit different, but that's it. Like the basic idea is still the same. So, all right, I'm going to go ahead and end it right there, I think. And I will see you in the next video where I explain how to do a chi-square goodness of fit test. All right, see you then.